Hi folks, welcome to today's lecture. I want to talk about data structure performance characteristics. The material for this video comes from my book, C# for Artists, second edition, chapter 14, and this section starts on page 400. You can get the book from pulpfreepress.com, and you can download the source code for free. Go to the support site even if you haven't bought the book. And you can, click on the support site link for C# for Artists, second edition, and download the code either, as a big zip file for the entire book or whatever chapter you want. The lecture, or I should say video previous to this one, talked about an introduction to the collections. Okay, and this lecture dives into the performance characteristics of data structures that make up or that work behind the scenes in various collection classes. And we start with the array. Arrays are covered in detail in the book in chapter 8. So if you've studied up to now through, and covered chapter 8, then you're familiar with arrays. Okay, so essentially, the characteristic of an array is, it's fast to insert and retrieve objects because the math to find each element is really fast to perform, right? It's quick and dirty. But if the array, if you wanted to insert elements into an array, okay, then you run into a potential performance bottleneck because you have to, let's say that you want to insert an element at a spot that's already occupied or that already points to an object. If you want to insert an element here, let's say into the second or the third element, then you're going to have to move these two objects, right? You don't move the objects per se. You have to move the references that contain point to the objects. You have to move those elements to the right. And depending on how many elements are in your array that point to objects, that could be, 2 or 3, which wouldn't take much time at all. Or it could be thousands, right? Depends on how many objects or how big your array is and how many objects it points to. Okay. So that's the downfall of using an array as a underlying data structure. The benefits are it's fast, right? As soon as the array is populated, you can get to each element lickety-split. Okay, but if you need to insert elements, then you take a potential performance hit, and this performance hit grows as the number of elements grow. Okay. The next data structure is a linked list. Now, another potential problem with an array is, you have to know how many objects, or an array takes up a certain amount of size, even if it contains just one element, right? Generally speaking, you don't create an array with one element in it. You usually create an array, it depends, 25, 30, right? So you're taking up space. If you try to anticipate how much how many elements you're going to need, let's say you need 1,000, right? Well, you create an array with 1,000 elements, and yes, each element in the array is only a 32-bit reference to an object, but you've got that much memory reserved for that array. And until you start pointing to objects, it's just soaking up memory, taking up space, right? Well, a linked list is a potential solution to that problem, okay? A linked list is represented by a data structure that we call a node. Okay, so we have a conceptualized image of a node here, and a node has a reference to an object, right? So this object ref here, this is what I'm talking about. This object ref in the center. This is the way it's pictured, right? But it would be like a structure. You'd have a pointer to an object called previous, a pointer to an object called next, and then you'd have a pointer to an object which would be the payload, which is what I'm calling object reference in this particular example. So this next pointer would be, pointing potentially somewhere, and this the previous pointer, next would have to point somewhere. Well, if you only had one element in the linked list, okay, you have other data. You have other fields within a linked list. I should say class, right? Called the head, the tail, right? The head always points to the first element of the linked list, right, or the first node. The tail always points to the back. So let's take a look here at a picture of a linked list, okay? So in this particular example, which is figure 14.8, we've got a head, right? We have a tail. Those would be like fields in a linked list class. And we have 3 elements or nodes, okay, that point to 3 different objects. And then these, the P, right, the previous points to, really the previous is you want to point the previous to the last object, right? If there's only one node in the list, then previous points to itself. If there's only one node in the list, then next points to itself. Well, here we've got 3 nodes in this linked list. So previous points to tail in this case. Tail always points to the last node in the list. Head always points to the first node in the list. And then, of course, this node's payload points to whatever object it represents, right? The second node, its previous pointer points to, the first node. The next field, right, of this node here, of the first node, points to this second node. The next field of the second node points to the third node. And the previous pointer of I say pointer, right? We're talking references in C#, but, really they kind of work like pointers, except for, you can't modify the value. Okay, so the previous reference here points to the second node, right? Because the third node points to the one before it, and then this one points to the one before it. This is an example of a circular doubly linked list, right? So we can go around and around and around one way, or we can go around and around the other way. All right. Now, so that's all fine and dandy, right? The problems. Now let's walk through the insertion of an element. So, and then we'll compare this with the way an array performs. So the insertion into, let's say we want to insert an object reference, right, or a node in between the first node and the second node. Well, we got to do a little bit of rewiring, right? So we come down here to the next figure, and so we have to bust up, what n points to for the first node. This n eventually has to be rewired to point not to its old node, but to the new incoming node, right? This P has to not point to the first node anymore. This P over here, and I'm on the third, I'm pointing to the third node, has to point to the incoming new node, right? And if you've never programmed, and you probably would never have done this anyway, right? Unless you've taken a data structures class. If you've never written a linked list, this used to be the acid test, or the surefire way. If you were ever confused about pointers in C or C++ or any language, you would never be confused after you've successfully written a linked list program, because you really had to stop and think about what you were doing with the pointers and where they were going, and to insert an object in the middle of this I call it wiring up, right? You got to wire up the pointers in order to point to the right nodes. And once you've done that in the code, then you're like, okay, now you're a real professional, to say the least, right? And once that insertion is complete, then we've got all the nodes pointing, all the references pointing to the right place. Head never, the only time head would change is if we inserted something at the beginning of the list. And the only time tail would change is if we, pointed at something different at the end of the list. Okay, so now we've got a linked list, right? The difference between the access performance of a linked list and an array is the array, you can locate an element really fast. So let's say that we had an array with a billion elements, right? Well, the time it takes to move all those elements, let's say you wanted to insert something, amongst these million elements, it would take a little time, right? And the time would be a function of how many elements you had to move when you do the insertion. And that would be O notation. You'd express that and it'd be some order, depending on the algorithm, on how long it took to actually move all those elements. And that time would be a function of number of elements for an array. Well, for a linked list, the insertion of a node into the list is a constant. You only have to wire up so many of these pointers, right? Handful, 1, 2. Well, let's see, we're going to count. So we got to wire up 1, 2, 3. Looks like 1, and then 1, 2, 3, 4, and then 5. So 6. I'd say 6 wire up operations, depending on whether or not you're inserting just in the middle of the list or something that requires changing the head and the tail. Okay. So so when I do the insertion, right, I gotta set this one. I gotta set the next here. I've got to set the previous there. I've got to set the next here and set the previous there. So that's 4. Okay. Now, so that's constant time. That's easy. You're only ever, no matter how, you're only ever going to insert one at a time, right? Even if you insert 100, you're only going to insert them, boom, one at a time. So it's constant time for each insertion. Whereas if you had a million elements in an array, a million might even not be enough. Who knows, right? Whatever the breaking point is for an array. If you inserted, and the array was practically not quite full, but, had a bunch of elements that needed to be moved, every time you inserted an element, you're adding more elements that need to be relocated potentially if you keep on inserting elements into the array. So that's just something. Now, but once you've inserted the element into the array, like I said before, the array is quick, right, to locate the element. Now, but that's not so with a linked list. With the linked list, unless you've got some type of indexing that gets you close to where you want to go, you usually have to start at the beginning of the list and then traverse the list to find what you're looking for. Okay. So that's an issue, right? That, it's fairly fast to make an insertion, but depending on the number of elements, it might take you a little bit of time, depending on the number of nodes in your linked list, to locate a particular object that you're looking for. And that's a potential downside to a linked list. Now, there's a couple of different ways you can mitigate that. One, let's go back up here because it's the diagram kind of breaks it up. Hash table. In answer to that, linked list problem is they've come up with hash tables. So a hash table is an array whose elements can point to a series of nodes. In other words, it's kind of a combination between a linked list and a hash table. Okay, I'm sorry, a linked list and an array. So, but instead of putting, so what a hash table does, it kind of reduces the size of the array, right? So your array isn't growing to this humongous thing, right? And you got to move a bunch of elements. So what you do is you try to come up with a hash function that allows you to insert elements uniformly throughout the array space that you've allocated. And, you can add more array space if you want, but essentially, if an object hashes to a particular entry in the array, then it gets inserted there. Now, if another object comes along, right, and you and its hash function says, okay, it goes in the same place, then it just gets tacked on to the end of the linked list. Essentially, it'd be a singly linked list here. So a hash table, it depends on what type of hash table as well, can actually be a good can have performance that's better than a linked list entirely, or an array, right? So it combines the best, I would say, the better characteristics of each. They all have limitations. Okay. I'm going to skip this chained hash table versus open address hash table. So let's talk about red-black tree performance characteristics. There's different types of trees, binary trees, right? But the red-black tree is interesting because it maintains balance when you insert objects. A red-black tree, like I say, is a special type of binary search tree with a self-balancing characteristic. So here we have pictured in this particular figure 14-14 is what a node of a red-black tree would look like. So you have a node, right, represented here by the object reference, and then you have a color that node can be. It could be red or black, all right? You have a left child and a right child, and you have a parent. So it looks like a try. It's like a try as one way to visualize it, where you've got a pointer that points up to the root node of the tree, which would be the beginning, and then left to right from there, you'd have elements. And you can kind of see the structure of a tree. In this particular case, I've inserted the integers 9, 3, 5, 6, 7, 2, 8, 4, 1 into a red-black tree. Now, you're like, well, how did you get that structure from a red-black tree? And it just turns out that there's a lot of great folks out there on the internet and a wealth of information regarding these data structure performance characteristics. And I want to draw your attention to one in particular. So this Professor David Gals at the University of San Francisco, Department of Computer Science, he has a website called Data Structure Visualizations. Okay, I put a link to this in this video. And if you click on the red-black tree, okay, you'll get the red-black tree animator, okay, or animation. So I'm going to go ahead and I'm going to insert these numbers, and you can actually see how a red-black tree, balances itself as different, numbers come in. So I'm going to start off with 9, okay? Hit 9. I'm going to click insert. So 9 comes in, and it's the root node, okay? And then the next number in the series, I'm going to enter 3. And I'm going to insert. So it comes in, it gets compared to the 9, and if it's less than the 9, it goes to the left. If it's greater than 9, it'll go to the right. So 3 was less than, so it gets inserted to the left. No rebalancing required. Now enter 5. So 5 is going to be less than 9, but greater than 3, okay? So I'm going to insert. We'll see what happens. It comes in, gets compared, and then it gets inserted, okay? Now there's a rebalancing because 5, so in other words, the whole purpose of the red-black tree is so it doesn't grow. Let's get back, okay? And let's do that again. We'll watch it one more time. And in fact, we'll slow down the animation. This is the beautiful part about this thing. So we're going to insert 5. There's a comparison that takes place, okay? It says, okay, it's greater than 3, and so it gets put there. But now the tree's unbalanced, so the tree has to do a balancing act. Okay, now if you'd like to see this type of code work in my other book, okay, C# Collections, a detailed presentation. In fact, if you look at the cover code, I actually, implement an algorithm from one of the MIT books, big old thick algorithm book that's like one of the tomes for computer science majors. And it's hard to find an implementation of that algorithm, but I actually implement that algorithm in this code, and you can actually, walk through the code and see the rotations take place and the balancing take place. And that's the C# Collections Detailed Presentation by Pulp Free Press. Okay, let's go back to the animation. All right, so the next number on the list would be 6. I'm going to insert 6. Gets comparison. It's less than 9, so it goes to the left. Okay, and then notice that the color's changed, right? All right, so now let's do that again. Let's do 7. So what happens is 7 is going to be greater than 5, 7 is going to be less than 9, 7 is going to be greater than 6, and then there should be a rebalancing take place. There we go. Comparison to 9, comparison to 6. It gets over there. Now we have to rotate to straighten out the tree. Here we go. So see how the tree maintains. In other words, it didn't grow too lopsided. And what's the benefit of that? Okay, well, the benefit is you're only ever 2 or 3 levels, depending on how many elements are in your tree, from finding what you're looking for. So the retrieval speed is quite fast. Okay, the insertion speed is a function of where this, the element that you're inserted, where does it go in the tree, and how many reordering operations and balancing operations are required. So the next one coming in is 2. Insert 2. Compared to 5 is less. Compared to 3, it's less. There we go. And that will stay like that. Oh, now we'll do 8. All right, 8 comes in, gets compared to 5, it's greater. Gets compared to 7, it's greater. Get compared to 9, it's less. All right. And there we stays like that. Now, let's do 4. It's greater than 3. Okay, so let's do 1. That's the last number in the sequence. Okay, so our tree is well balanced, and that's a great animation. What a great job. Okay, and so essentially it looks like figure 14-15 after all the insertions take place. All right, stacks and queues. All right, stacks and queues are 2 data structures that you should encounter a lot in your study of computer science. So a stack operates kind of like a, how would you say, a paper plate dispenser or a paper cup dispenser, right? In other words, there's, for a stack, it's got a last in, first out. So, you take a paper cup and you stick it up in the paper cup dispenser. That was the last one that was inserted. Well, when you go grab a paper cup, you grab that one that you inserted. So first in, last out, right? Or last in, first out. LIFO, okay? That's a property of a stack. And you've got push and pop for your operations. Okay, so a push means you're pushing a value onto the stack. A pop means you're taking a value off the stack. And there's a peek operation as well, where you can take a look at values that are on the top of the stack. And then you have a queue. So a queue is your typical, you usually think of a queue as waiting in line for a bank teller, or you queue up at a grocery store, right? Yeah, bank teller is a good analogy, because usually you have a line and you might have 5 or 6 bank tellers, right? And you got a big line of people, and then you come into the line, you're last to come in, and the person that came in before you gets the next choice of the open bank teller, right? And we can animate these as well. So if we go back to Let me click here first and then click on, there we go. We can actually step back and we can click on a stack, okay? So here he's got a couple different versions of stack. We'll take a look at the array implementation of stack, okay? And let's try this. So we'll just pop some numbers in here, right? So we'll pop 9. Well, we'll push, I should say. We'll push, okay? So the top of the stack goes to 0, okay? Now, so you see that, right? Top is a pointer or a variable that points to the next element, right? So the top of the stack is 1. Well, there's 1. So let's go ahead and do another one. 3, push. Okay. So now we'll pop a few more. We'll just pop a bunch of 8s. Push, I should say push. Oh, it's not letting me push but different values. So 5. There we go. All right, now if we pop, see what happens here. There we go. Okay, we'll pop the next value. Pop the next value. Okay, so you get the point. Now let's see how he's implemented the linked list implementation. All right, so like I said, right, you have this space available for an array. If we go back to the array, so you've got no elements in your stack, but you've got, in this case, it looks like there's 30 elements have been reserved for, values in your stack, but you're not even storing anything in there. So you've got memory reserved, but nothing in the stack. Whereas if we use a linked list, we've got nothing reserved and it's not pointing to anything. So let's push a value. So there we go. So that showed the creation of a node. Okay, and then this is a pointer to that first node. So that's pointing to the top of the stack. So we'll do 7. There's another node gets created. Okay, now top points to that one, and then it's rewired the next to point to 9, right? So let's do 6, push. Okay, there's a new node. Top points to the new node. And then this next element, right, points to the next element on the stack, and then this element points to the other next element on the stack, like that. Now, if we pop, right, we pull off the 6, and then we got to rewire top to point to 7. We pull out the value 6, it's popped, and there we go. Okay, so that's a great animation there. Okay. Let's go back to the book. Now for Q, all right, so let's, the Q has NQ and DQ operations. Let's check those out in the animations and see what he's got. Okay, so Q, we'll do an array implementation first. Okay, so we've got the head and the tail for the Q. So we're going to NQ9. 9 comes in. Okay, that's the value. Okay. Now 1's the tail, head's the 0. 8. All right. 4. All right. Now let's do some dequeues. So if we're dequeuing, right, since it's a queue, is 9, right, has been there. So these guys are coming in later. So these guys are at the back of the queue. So the first element that will be pulled off will be 9. So we're going to dequeue. So we pull off 9. Now head points to, okay. Now you can see here, if we keep on going, we're either going to have to add on to this array, or it's going to have to figure out that, it keeps on going round and round. So let's speed up the animation. Let's see what happens. All right, I'm just putting some stuff in here, different numbers. All right, let's do some more. Okay, 3 more to go. Now let's go ahead and dequeue. And okay. Now let's enqueue a few more. All right, so now now see where tail? Tail's like, oh, hey, we got free space back here. So this is acting like a ring buffer. Let's see what happens if it fills up. Okay, it looks like if he's only got one space, and since the fourth element, or the fifth element, number 4, indexer, is occupied, it's done. So I have to dequeue to free up a space, and then I can enqueue the 5. Okay. So yeah, that's a nice. That's very nice. Okay, let's go to back to the animations and take a look at Q as a linked list. Okay, so we got head up here and we have tail down here. So let's go ahead and enqueue. All right, so there's only one element, so tail and head point to the same thing. Let's do another one. So tail keeps on pointing to the end and head points to the beginning of a queue. All right, beautiful. So notice, I mean, we don't have a limitation like we did with the array. I mean, the array, you know, either we would need to resize the array, right? But if the array filled up, the queue filled up, then you couldn't insert any more stuff. Here, you're not likely to stop. You know, you can put as much stuff in as you want because there is no array. So it doesn't need free space, right? You're limited by the nodes. Now we dequeue. So there we go, dequeue. Beautiful. Okay, yeah, that's a great animation. Okay, back to the book. So an array is a contiguous allocation of objects in memory, right? An array-based collection offers quick element access, but slow element insertion, especially when the collection's underlying array must be resized and elements shifted in order to accommodate an insertion. A linked list consists of individual nodes, right? that are linked to each other via references. And then in order to find something on the list, you got to traverse the list, starting at the beginning, right? Okay, then we had talked about red-black trees and how they rebalance themselves. And we talked about stacks and queues, and we saw the animation. And one more time, I want to give a great a shout out to David, assistant professor up at the San Francisco University of San Francisco. And what a great set of animations! Thank you. Okay, and that's it for this video. Next lecture will be navigating the .NET Collections API. Now, you think that's a trivial topic. It's not, because there's a lot to the .NET Collections API, and it's worth dwelling on and exploring. So I'll see you in the next lecture, and thank you very much.